Hello, welcome back to physics. We're working on acceleration problems. Now we're going to kind of put everything that we've learned together and solve a few fairly simple problems in acceleration. So what we have here on the board is a velocity time curve. You can see that it's kind of a weird, jagged looking curve, but what we're asked to find is what is the instantaneous acceleration at t is equal to 3 seconds, and then find it again at 7 seconds, and find it again at 11 seconds. So what we want to do is we want to figure out what is the instantaneous acceleration at 3 seconds, so that's going to be basically right here. And then again, we're going to do it at 7 seconds, which will be between here, so we'll kind of go up roughly to there, something like that. And then 11 seconds, which is 10, 11, 12, so that's roughly right around here, something like this. All right. Now, it's always dangerous when I do these problems and I've drawn a freehand graph, so forgive me a little bit if my lines are crooked or whatever, but the point is the logic behind it, because if you draw a perfect graph and measure everything, it'll all come out perfect. What I'm trying to teach you is the logic behind what to do. So first of all, they asked you for the instantaneous acceleration. So when they asked you for instantaneous anything, you should be thinking, oh, that's the slope of the line tangent to the curve, right? So if it was a wiggly curve with humps and hills and valleys, then you would have to go draw a line tangent as best you can and find the slope of that line. But this curve doesn't have those smooth hills and valleys. It's a jagged thing. So what you really need to realize is that basically the slope of the line tangent, like in this segment here, is this line, right? And the slope of the line tangent over here is this line here, and the slope of the line here, the slope of the line tangent to the curve is this line segment over here. And I can more easily demonstrate that by kind of even a simpler example. I mean, when you think about it, let me go off to the side and do a totally separate problem, or a totally separate little aside here. Let's say that I have another curve over here. So this is going to be time, and this is going to be, velocity, as it always is. All right. Let's say that I have a curve that looks something like this, very curved, right? And I want to figure out what is the acceleration at point A right here. So it's a curved thing. The slope is changing all the time. So what I've been telling you to do over and over and over again is, well, you have to get a ruler out, or in calculus you'll calculate it, but in graphically you would get a ruler out, and you would find the line that just kisses that curve, tangent, meaning it touches only at that point. And then you do rise over run and figure out what the slope of that line is. That's going to be what we call the acceleration, the slope of the velocity curve. That's going to be the acceleration. All right. But what's going to happen, so this is, for this curve, it's very exaggerated here, okay? What's going to happen if I flatten that curve out a little bit? Let's draw another curve. We're going to hold this point the same, point A, let's call it. Then let's draw another curve, not quite so dramatically